Definition 2.6 is the definition of a Markov chain. For random variables x1, x2 up to xn, where n is bigger than or equal to 3, x1, x2 up to xn forms a Markov chain in this order if px1, x2 up to xn is equal to px1, x2, px3 given x2, all the way to pxn given xn minus 1. If px2, px3, all the way to pxn minus 1 is bigger than 0. Note that if these probabilities are not bigger than 0, then the conditional probabilities are not defined. Otherwise, px1, x2 up to xn is equal to 0. Here's a remark. x1, x2, x3 forms a Markov chain in this order is equivalent to the condition that x1 is independent of x3 given x2. Proposition 2.7 says that x1, x2 up to xn forms a Markov chain in this order if and only if xn, xn minus 1 up to x1 forms a Markov chain. Basically, it says that if you have a Markov chain in a certain order, if you reverse the order, then it is still a Markov chain. The proof of this proposition is left as an exercise. Proposition 2.8 says the following. x1, x2 up to xn forms a Markov chain if and only if the following sequence of Markov chains holds. First, we have the Markov chain x1, x2, x3, and then the Markov chain x1, x2 as a pair, and then x3 and x4. And all the way to the last Markov chain x1, x2 up to xn minus 2 as a group of random variables, and then xn minus 1, and then xn forms a Markov chain. The proof of this proposition is left as an exercise. Proposition 2.9 says that x1, x2 up to xn forms a Markov chain if and only if px1, x2 up to xn can be factorized as some function f1 of x1, x2, f2 of x2, x3, all the way to fn minus 1 of xn minus 1 xn. For all x1, x2 up to xn, such that px2, px3, all the way to pxn minus 1 is positive. Note that proposition 2.9 is a generalization of proposition 2.5 that we have seen before. Proposition 2.10 is about Markov subchains. This proposition looks a little complicated, but in fact the idea is very simple. Let n sub n be the index set containing the integers 1, 2 up to n, and we let x1, x2 up to xn form a Markov chain. For any subset alpha of the index set, denote the collection of random variables xi, I in alpha, by x alpha. Then, for any disjoint subsets alpha 1, alpha 2 up to alpha m of the index set such that k1 is less than k2 is less than all the way to km, for all kj in alpha j, j equals 1, 2 up to m, we have the Markov chain x sub alpha 1, x sub alpha 2, all the way to x sub alpha m. That is, a subchain of x1, x2 up to xn is also a Markov chain. We leave the proof of this proposition as an exercise. The condition that these disjoint subsets alpha 1, alpha 2 up to alpha m need to satisfied is illustrated in this figure. If this condition is satisfied, then we have the Markov chain x sub alpha 1, x sub alpha 2 up to x sub alpha m.